All right, guys, so let's move on to number 20 from our Unit 7 study guide. The rest of this study guide is pretty much just devoted to area and volume questions. So let's go ahead and take a look at this one here. So we've got our two functions here, and we're being asked to find the area of the region enclosed by these two curves. Now you could do it by hand, or you could do it using a graphing calculator. For this test, I'm really probably not really too concerned about which method you choose to go with. So let's go ahead and go with the graphing calculator. So the first thing I'm going to do is we're going to put these two equations into our graphing calculator under y1 and y2. Be careful for the fraction when we put those fractions in parentheses so that our calculator gives us a correct answer. So now, if I wanted to calculate the value of this area between the curves, what we're going to do is we're going to make an integral. Now we're going to do y1 minus y2. Now technically you should have the one that's greater, or in this case above the other function, come first, but we don't really know without graphing it, and we could graph it and figure it out, but quite honestly it doesn't matter because I've told you guys that we can just throw some absolute value bars on there like that. And this is one of the problems where it's kind of nice because they just tell you what they want you to integrate to and from. They want us to go from -2 to -1. And that doesn't necessarily mean that the functions are intersecting at those points. Sometimes they just want us to go from one point to another. So just to kind of bring it down to earth a little bit and give it some context, let's just take a look at what it actually does look like, even though we really don't care. Now what we're doing is we're integrating from -2, which is like about here. So if I were to go straight up and straight down, and then -1, straight up and straight down, what we're finding is this little area right here between the two curves. And now that I've graphed it, I can see that my y1 function, the quadratic, is higher than the linear function, which I typed in as y2. So the way I set it up, technically, yes, the y1 should come first. But like we said, it doesn't really matter which one comes first if you use the absolute value function. So get back to our original slide here so we can calculate the answer. So actually what we're going to do now is we're going to type that function in to our calculator. So we're going to go to second, quit, so we can get back home. We're going to push math. We're going to push 9. We're going to push. Matter of fact, I think I'll just stop telling you what I'm going to push. I'm just going to push it because you guys can see down here what I'm typing. Absolute value in there, right? We don't care about the order. Right. And then we're going to go and put a dx right here, and there's the area between the curves. Okay. Not too bad, right? Pretty straightforward. All right, let's go ahead and take a look at our next question here. Now you'll notice on this one, find the area enclosed by the curves. I wonder how it's worded differently. All right, so for this one, they're not telling us the starting point and the ending point for the x values. So in other words, we need to find where these functions are intersecting. So compare and contrast number 21 with 20, right? On 20, they're telling you the x values to use. On 21, they're not. And so when they don't tell you those x values, you actually need to find where they intersect. So we're going to start by graphing it, and then we're going to find where they cross. All right, so we type it in, and just want to reemphasize this to you guys. There is a difference between the negative button and the minus button, okay? Minus is when you want to do subtraction. Negative is if you want to make something negative. The way we use them in math, it doesn't matter, but calculators seem to care. So if you were to put a minus, this gray button here, when typing this, you're going to get an error symbol. We want a negative, so make sure you're getting those symbols correctly. Anyway, we're going to graph it, and luckily we could see that they're crossing twice here, well, actually 3 times. Once here, and once here. Now, if I was doing the integral by hand, I would have to do 2 separate integrals. Basically, what we're going to be doing here is we're going to be finding the area between the two curves, which would be this little piece right here, and would also be this little piece here, and we would have to do an integral for each of the area pieces. But since we're doing it on a calculator, all I need to do is I just need to make sure I find the leftmost intersection point and the rightmost intersection point, and we're just going to integrate from that point on the left to that point on the right. Okay? And we really don't care about the order if we just use the absolute value bars. Okay? All right, so let's go ahead and find those intersection points then. So how do we do that? Math? Nah, that's not what we do, Mr. Bailey. That's not what we do. So I'm gonna get out of there. My graph here. We go to second, trace, 5, scroll over to that point of intersection, and we're going to put enter 3 times. And there it is. That's kind of easy to remember, so I'm not going to store that value. I'm just going to write it down. Not the great answer. No need to store it. I know it's -2. It's good enough. I'm going to repeat that process now. Find the other intersection point. Oop, too far. Right about there. That's about as close as it's going to let me get. And that one's also a nice number, so we're just going to put it right there. And this is what I'm going to type into my calculator. So let's do that. And you'll notice I typed it backwards from what I wrote here, but once again, the absolute value bars kind of make that irrelevant, so we should get the right answer no matter what. So we're getting 21.833, it looks like. Stats you guys can see a little better. There you go. Moving on to the next one. All right, number 22. Find the area of the region enclosed by these curves. Okay. Now you'll notice that these equations are written in terms of y, and they're giving me my integral limits from y equals 0 to y equals 4. So they want this to be an integration with respect to y. So let's go ahead and do that. We're going from 0 to 4. We'll call this one x1 minus, we'll call this one x2, and we'll be integrating with respect to y. And you're just going to type this into your calculator, but the only difference is that when you do type it into your calculator, we have to pretend like the x's are y's and vice versa, because our calculator does things in only one way. But you'll get the same answer either way. Okay. Now, if you were doing this stuff by hand, you would need to know which one of these functions is farthest to the right, because that's the one that would be greater, and that's the one that would have to come first, and you wouldn't use absolute value bars, right? And the way you would do that is just pick a point and plug it in and see which one gives you the greatest x value, the one that's farthest away from the other one. So there you have it. Let's go and see what the calculator would render for us there. A little bit. Looks like they're getting 5.33. All right, moving on to the next one. All right, so here's another one. We're integrating with respect to y again, because once again, we have functions that are in terms of y as opposed to x. So that means we're integrating with respect to y. And since we're going to use our calculator, we only do one integral. But if we were doing this by hand, we'd have to do one integral for the first area and then another integral for the second, making sure that we put the one that's farthest to the right first and the one that's farthest to the left second when we do our subtraction. However, we don't care about any of that right now. I'm just going to call this one x1, this one x2, and I'm going to go ahead and just put those in parentheses like that. Slap some absolute value bars on there. And then we're going to, remember, since we're going with respect to y, it's important you remember we integrate from bottom to top. And so we're going to put our first x value here, I'm sorry, not x value, y value, which is -3. And we stop at this y value up here, which is +2. And you would, once again, when you type this in on your calculator, we're just going to type it like the x's are y's and the y's are x's, because our calculator only does it one way. And so this is what you would actually type in on your calculator. but it doesn't matter. This is what you would write on your paper if it was like an FRQ or the test or something. But this is what you would type in on your calculator to get the answer. So let's take a look at what that answer is. 21.083. All right, let's move on to the next problem here. The base of a solid is the region enclosed by the ellipse. Cross sections perpendicular to the x-axis or squares. So cross sections, when you see that, that's the one where we're going to be visualizing this thing as being laid down flat, and we're going to be stacking shapes, in this case squares, on top of it, right? So that's the kind of problem we're dealing with here. Now, in this case, we do need to pay close attention to, for these cross-section questions, what it's perpendicular to. When the shapes are going to be perpendicular to the x-axis, that means they're going this way, because that way they make a 90-degree angle with the x-axis whenever you put them on top there. Which means that the base of the shape goes from bottom to top, and when you're going from bottom to top, that's a dx problem. So we need to be doing this in terms of x. So once again, we see the cross-section problems. If it says perpendicular to the x-axis, that means we're integrating with respect to x, and our equations need to be in terms of x. If this is perpendicular to y, then the opposite is true. All right, so the first thing we got to do is we've got to get the y by itself, because we want to get the equation to be in terms of x here. So I'm going to take this equation here, x squared over 36. And I'm going to minus the x squared over 36 on both sides, which will give me this. Then I'm going to multiply everything by 9, which would give me this. The x squared over 36 becomes x squared over 4, because when you multiply by 9 on everything, the 9 over 36 reduces to 1/4. Okay, and then finally we're going to take the square root on both sides, which gives us this. Now when you take a square root, you always get a plus and a minus. And we want to remember that, of course, the plus means the top half, and that the minus means the bottom half. And we're trying to find the distance between the top half and the bottom half, which means you're going to subtract the positive square root of 9 minus x squared over 4 from the negative version of the same thing. And we've seen this quite a few times before in the lesson at that time, but you have double negatives there, and double negatives become positive. And when you add one radical to something that's exactly like it, that means you just have this. And so what this ultimately gives you here is this gives you the base, we call it. The base of our shape. It's the distance from here to here. Or in other words, for this shape that we're looking at, it's the bottom half, right? Now, since we're dealing with a square, the next step after you find the base is to find the area of that square. Now, as you guys know, the area of a square is going to be base times height, and they're the same when a square, so it's base times base, really. And so what you really end up with is that the area of the square is equal to this base length here. Squared. And then our final step to turn it into a volume is to find a bunch of these squares and add them all together so that we create this three-dimensional image that kind of looks like, what you'd say this looks like. There it is. So to do that, we integrate from our starting point to our ending point. Now, when you're integrating with respect to x, you start on the left and you end at the right. And so that's going to be from -5, it looks like, no, -6, I'm sorry, -6 to +6. And then you put the area that you're integrating over here. And then put your dx there. From there on out, it's just basically a calculator question. So let's go ahead and see what we get there. All right, and you should be getting about 288 would be the volume of the shape that they're talking about there. All right, let's go ahead and move on to the next problem here. Going to have a couple of these cross-section problems now. The base of a solid is the region enclosed by these two curves. So now we're dealing with two curves, right, instead of just one. The cross sections are perpendicular to the x-axis. That's an important little word because that means we're going to be integrating with respect to x, and we want our equations to be in terms of x as well. And the other key piece of information that we want to focus on is the fact that we're dealing with rectangles with heights that are half of the side. So step one is to find the base of the shape that we want to be stacking on top of this area. So just as a visual, I'll go ahead and draw the flattened version of this real quick. Might look something like this. And my goal is I want to be stacking rectangles on it so that they're perpendicular to the x-axis, and they would look something like this. And so as you guys can see, the base of the rectangle is going to be the length that goes from the top of the first curve to the bottom of the second curve. So our base in this case, which is where we start off at, the base of our shape is going to be the distance between those two functions. So it's going to be, if I call this one y1 and this one y2, the base is going to be the distance between y1 and y2. Now, technically, you want to make sure that the one that's on top comes first. This actually is the y1 function at y equals 4, and this one's the y2 function, which is the quadratic. But once again, just to be safe, you can always just put an absolute value bar on those so that you don't screw it up and accidentally guess wrong, right? So there's my base length of my rectangle. Now, we're going to move on to the area, which we're looking for the area of a rectangle. Now, as you guys know, the area of a rectangle is base times height, right? Now, we already know what the base is. The base is y1 minus y2, right? My height, though, according to the problem up here, is that the heights are half of the base. So it's going to be half of y1 and y2. Left my absolute value bars off there. So my height is the same thing as the base, just with a half in front of it. And so when you simplify this, you end up with 1/2 absolute value of y1 minus y2 squared. Okay? And so there's your area. And then finally, in step 3, we do our integral, because at that point, you want to add together an infinite number of little rectangles with these areas, starting from the left and ending on the right, because we are going to be integrating with respect to x, because we are doing it perpendicular to the x-axis. So from the left, that's -6, and from the right, that's 6. And we're going to be plugging in this little formula right here. And that's what we'll type into our calculator. Let's see what we get as a result of doing that. And you should be getting 51.2. Notice they put the half in the front. I left it inside you could put it in the front. It wouldn't matter. It's a constant multiple. You're allowed to do that. That was property 2 back in Unit 6, I believe it was. Also, they actually write the functions in there, whereas I just put y1 and y2. And just be careful, you're allowed to call them y1 and y2 on an FRQ if you want to, but you do need to make sure that you define them as that before you start using variables. Otherwise, you don't get credit for that. You gotta be careful. But anyway, the answer is 51.2. Let's go ahead and move on to another question here, number 26. Same question, really. We're still going perpendicular to the x-axis, and actually the shape is almost the same too. It's a parabola and a linear function on top. So a lot of it's going to look the same. So the only difference is the fact that we're stacking a different shape on top. So that'll happen in step 2. So in step 1, we want to find the base length. So if you were to lay this thing down flat, it would look like that. And the goal is that I want to be setting semicircles on top of it that are perpendicular to the x-axis. That would look something like this if I were to do that, right? So there's the idea. Now, the base is the distance from the top function to the bottom function, right? And that base is equal to y1 minus y2, where I'm going to call this one y1 and I'm going to call this one y2. And just in case you're not watching me do every problem, when you do this, technically you would want to make sure that the one that's on top comes first, and that is y1. So it's y1 minus y2, not y2 minus y1. But I've also told you, since we're doing this on our calculator, we can kind of avoid the problem by just putting absolute value bars on them, and it doesn't matter at all. So there's my base, and now we're going to move on to step 2, and that's where the difference of this question comes into play as opposed to number 25. We're trying to find the area of that semicircle that we're stacking on top of it. Now, I gave you guys a formula for the area of a semicircle. It's going to be pi over 8 times the base squared, and my base is y1 minus y2. Simple enough. Step 3, we're going to go ahead and integrate now, because we want to add together all the little semicircles that would be infinitely many from one end to the other, starting from -2 and ending at +2, because we are integrating with respect to x, so we integrate from left to right. If you want to put the pi over 8 in front, you can, or you can leave it in the integral. It doesn't really matter. Oops, dy, Mr. Integrating with respect to x. Okay, there you go. And that'll tell you the volume of the shape that you would get by stacking those shapes right on top. And that comes out to be 0.838 cubic units. All right. Moving on some more. All right, we're going to be stacking shapes again. Couple of differences. This time we have to solve for either x or y. And the one that we solve for is going to be determined by what we're integrating with respect to. And since we're doing cross sections that are perpendicular to the x-axis, we're looking for getting the y by itself, so our equations are in terms of x. So step 1, let's find our base. So since I'm stacking shapes on this thing that are whose base is going to be perpendicular to the x-axis, that means it's going to be a vertical line like that, because that's perpendicular to the x-axis. And when we go vertically like that, we want to get the y by itself. So first thing I would do to this equation is I would minus the x squared over 16 on both sides. So if I did that, I would end up having something that looks like this. Then I would multiply everything by 9. And we haven't seen this happen yet in our notes. Oops, sorry about that. Getting ahead of myself. We haven't seen this happen yet where you end up with a number here. I'm not too sure it actually will really matter too much since we're doing this on our calculator, so that's okay. Let's keep going. Next step is to go ahead and take the square root. Oh, this should be a 9 by now. So we end up with this now. And we want to remember that when you have the y by itself, the positive refers to the top half of the circle, and the bottom refers to the bottom half of the circle, right? And so the base was what I'm trying to find right now, is the distance between the green and the whatever color that is, tan or peach. So it's going to be the square root of 9 minus square root of 15 minus a negative square root of 9 minus 9. And the double negatives just become a positive, and when you add two square roots that are identical, you basically just get 2 times that square root. And that would be our base. So that's the end of step 1. That's the distance between the top and the bottom half. So now we move on to step 2. Step 2 is where we find the area of the shape that we're stacking on top of it. And so In this case, we want to be stacking equilateral triangles on top of this shape. So to visualize it, it would look something like this. We have our little oval that looks something like that in the base. And what I'm going to be doing is stacking equilateral triangles on top of it so that the base of that equilateral triangle is here. So that would look something like this if I was to be stacking a whole bunch of them. And what I want to do is I want to find the area of each one of those. Now in step 2, to find that area, I gave you guys a formula for the area of an equilateral triangle. The formula for the area of an equilateral triangle is going to be the square root of 3 over 4 times the base squared. Okay, and so that's going to be 3 over 4, and the base is, as you guys know from step 1, 2 times 9 minus. All right, and that moves us on into step 3, where we're going to be asked to find the volume of the shape that would result if we stacked an infinite number of triangles on top of that. And so to do that, we're going to integrate from left to right, because we are integrating with respect to x, our area formula here. And you could put the square root of 3 over 4 inside the integral or outside. Doesn't matter. That's a property of integrals. You can move those around if you want to. I'm going to leave mine inside for now. And if I were going to be doing this problem, you want to be careful about how you're entering this into the calculator. I mean, this is a big, ugly number, right? So, I mean, what I would do is I would type this whole thing in here under the equation y1 minus y2. I'm sorry. I would type that whole thing in there under y1 in my calculator. And then what I would do is I would type this into my calculator, the rest of it really. But with the square root of 3 over 4, you're going to want to be careful to put that in parentheses, because anytime you have a fraction, you want parentheses. And so this is how I would type it in my calculator. It's just that the bigger and uglier these equations are, if you don't store the equation separately, it's very likely you're going to end up missing a parenthesis and or type something wrong. It gets really confusing. So I like to store the equation myself under y1 and just enter it like that. But it's up to you. However you want to get that integral into your calculator is fine. But regardless, you should end up with an answer of about 83.138. So what is significant about number 28 is this statement right here. We're now going to be doing perpendicular to the y-axis. So number 28 is our first step in a direction different from the past few problems we've been doing. Everything we've been doing up to this point has been perpendicular to the x-axis with these cross-section problems. But now we want to go perpendicular to the y-axis, which means that I want to stack some semicircles on top of this shape. So I'm going to give you guys a visual here. This shape would look something like this, right? If you were to lay it down flat. And what I want to do now is I want to stack some semicircles on there, but here's the catch to all that. My semicircles are going to be perpendicular to the y-axis. So the base of the semicircle is here, and it's going to rise up off the top like that. And then so on and so forth as we work our way back. So we're going perpendicular to the y-axis. Now, when you're going perpendicular to the y-axis, you are going to be doing things in terms of y. So I need to change this equation so that instead of being y equals an equation with x in it, I need to change it to x equals an equation with y in it. So we have to get x by itself. Okay, so let's go ahead and do that really quick. So step 1, for the base, we want to go horizontally, and when we go horizontal, we need to get the x by itself. So the first thing I would do to get x by itself is I would subtract the 1 on both sides. Then I would multiply everything by 9. Then I would get rid of this negative by multiplying everything by a negative. And then I would take a square root on both sides. And when you take a square root, don't forget you do get a plus and a minus. All right, so now I've changed it from an equation where we have a y equals an x squared over 9 into an equation where we have an x equals an equation with y in it instead. Now remember, when you get this plus and minus situation, and it's in terms of y, the plus means the right side of the graph, and the minus means the left side of the graph. And so the base is the distance from the green side to the peach colored side there. On my screen it looks peach. I don't know what it looks like after it gets uploaded on YouTube. The color over here looks peach to me. So we always do right minus left. So it's going to be right, the positive one, minus left, the negative one. And no surprise here, we've seen this many times. We have this double negative situation, so it just becomes a plus. And then when you add two square roots together that are exactly the same, you just get that square root with a 2 in the front. And so there's your base length. That's the base of the shape that I'll be stacking on top of here, perpendicular to the y-axis. Okay, so that's the end of step 1. All right, moving on to step 2. Step 2 is to find the area. And so for that one, we need to look at the shape that we're stacking. And as we said already, we're stacking a semicircle on top of this shape, on top of this base. And when you're stacking semicircles, the area of a semicircle is, as I've told you, pi over 8 multiplied by the base squared. In this case, my base is what we just found in step 1, the distance between the left and right half, which is given by 2 times the square root of the negative 9y plus 9. Then finally, we're stacking an infinite number of semicircles on top of this shape, and we're going to add them all up, and that's where the integral comes into play. But you got to remember, this is another thing where when you're integrating perpendicular to the y-axis, that you're going to be integrating with respect to y, which means that your limits of integration are going to be the bottom and top of your graph rather than the left and the right of this graph over here. So the bottom value is 0 for y, and the top is 1 for y. And then this whole formula here is what's going to go inside of the radical, or the integral there. So I'm going to put the pi over 8 in front because it's a constant multiple and because I don't have a lot of room. But you don't have to do that necessarily. And there you go. So there's your setup, and there's our answer. All right. So 7.069. So a lot of this is being done in the calculator, so make sure that when you guys are doing this that you are at least showing me your setup on your paper, but beyond that, calculator is good enough. All right, let's go ahead and move on to another question now. The base of a solid is the region enclosed by this semicircle and the x-axis. Cross sections are once again perpendicular to the y-axis. So this equation is not acceptable. I need to get this to be an equation that's in terms of y, and that's going to help me find my base. So step 1, my base is going to be found by taking this equation and getting the x by itself. So the first thing I would do is I would square both sides to get rid of the square root. The next thing I would do is I would subtract the 16 on both sides. The next thing I would do is I would multiply everything by a negative to get rid of the negative off of the x squared there. And then the final thing I would do is take a square root. And we don't want to forget that when you do take a square root, you get a plus and a minus. Now, when we do that, the positive represents the right side, and the negative represents the left side. And I want to find the distance between those two sides, because when I'm laying this shape flat like this, what I'm going to be doing is I'm going to be stacking semicircles on top of that so that they're perpendicular to the y-axis, like that. And so the base of my semicircle that I'm stacking on top of here is going from the left side of the graph to the right side of the graph. And so that's going to be the distance between these two halves. So we're going to do the right half, which is the positive one, minus the left half, which is the negative one. And when you do that, you get your double negatives, which just become a positive. And when you add together two identical radicals, you just get that radical with a 2 in the front. And there's your base. So now we're ready for step 2. In step 2, we calculate the area of the semicircles that we're going to be stacking on top of that base. And since we're stacking semicircles, the formula I gave you guys for that is pi over 8 times the base squared. And the base is, as we've already said, this. Step 3 is to add together the infinite number of little semicircles that we're going to stack on top of that shaded area so that it turns into a solid, and that's done by integrating. Now, since we're integrating with respect to y, that means we're integrating from the bottom of the shape up to the top of this base shape here. So the bottom is y equals 0, and the top is 4. So we're going from 0 to 4, and this, we're integrating or adding together all of these little areas. And I'm just going to put the pi over 8 in front because it's a constant multiple. Save myself a little space inside. You don't have to put it outside, but I choose to. Constant multiples can come out of the radical of the integral like that. And there you have that. So there's your formula for the volume and what you would type into your graphing calculator. Once again, you know, how you type it in is up to you. You can literally type it just like this. I think that it would probably be a little bit less confusing and less prone to error if you took the time to change this into just y1 by typing it into your calculator as y1 and then putting this in parentheses. So what you end up typing into your calculator is pi over 8 in parentheses with an integral here, and then all you have here is y1 squared. Just much simpler and therefore less likely to have errors. Oh, and by the way, since we're typing into our calculator, you're going to have to put an x here, but just remember that's still really a dy. So this is what you want to write on your paper, but this is what you would type into your calculator. They'll give you the same answer. All right. Next. All right, so we're done with cross-section problems, and we're going to move on to the volumes of rotation now. Okay, so the first thing we want to take note of is what axis we're rotating around. We're rotating around this line right here, which is the line y equals 1. And when you rotate around a horizontal axis, your integration is going to be with respect to x. So we want to keep that in mind. And also you want to remember that your radius is the distance from your curve straight down, or in some cases straight up to the axis of rotation, depending on which one is on top. So let's go ahead and begin here first by finding our radius. Once again, if you want to use absolute value bars, just to make sure that you're not doing the order wrong. In this case, we have the parabola represented by this function here on top. I'll call it y1 minus the axis, which is the actual equation here, 1. And so that would be my radius. And as we spin this around, each radius along that curve will trace out a circle with an area of pi r squared. And then after that, you go ahead and integrate from your starting point, which on the x, the farthest point to the left would be 0, farthest point to the right would be 1, and I'll just go ahead and put the pi out front here. and I have a little boo-boo here. Let me fix something. This is my r, so I shouldn't have had an r right there. I should have just had a square right there, and therefore right there. All right, and then we go ahead and punch that into our calculator, and you should be getting something like 1.76. Move on to our next question. All right, now notice this time we have a vertical axis of revolution, and when that happens, we're going to be integrating with respect to y, and also your functions need to be in terms of y, which, as you can see, it's already been done for us, so that's kind of nice. So when you're doing this, your radius is the distance from the function, the main function that they give you, from the axis, which is right here, of rotation, and it's going to be a horizontal line, right? And that distance is found by doing the function farthest to the right minus the function on the left. And so that's going to be, call it x1, minus the axis of rotation, which is -2. And if we simplify that, we just get x1 plus 2, right? And as we rotate this thing horizontally, which is what we're going to be doing, it's going to trace out a circle with an area of pi r squared. Oops, a little square there. And then if we were to just integrate that with respect to y, because we are doing a vertical axis of revolution, from top to bottom, that's how you do vertical integration, is from bottom to top. So that's going to be from 0 to 2. You're going to get an area of your circle, which would be 53.617. And as you are punching this into your calculator, just so you know, here you're going to have a y1, and that would be the function that you type into your calculator, and you would have an x here. And then this would be an x instead, because as you know, our calculator doesn't do things with respect to y, it only does things with respect to x. So whatever's an x, we call a y, and vice versa. All right, let's go ahead and move on to number 32. All right, we're back to a horizontal axis of revolution, and this time my axis is the x-axis. So we're going to have my radius first. The radius is the function, which in this case is 2 over x. I'll just call it y1. That's what I would type into my calculator. And the axis is 0 because we're rotating it around the x-axis. Therefore, that would be my radius. And as I rotate it around the x-axis, it's going to trace out a circle with radius pi r squared, where r is my function in absolute value there. And then since we're going on a horizontal axis of revolution, we're integrating with respect to x, which means that we're going from left to right. And these values up here are the starting and stopping point. So this is 1/3, and this is, so we're going from 1/3 to 2. And once again, we're going to go ahead and take a look at the answer here, and we should end up with 31.416 as a final answer. Let's go ahead and move on to number 33. Once again, we're back to a vertical axis of revolution, which means that we're integrating with respect to y, and our equation should also be in terms of y. Your radius will be the distance from your curve, which is this parabola here, to the axis of rotation. So this horizontal distance here, or anywhere really along that curve. And we're going to be rotating it around that axis. I'm going to trace out a circle as we do that in a horizontal fashion, because we're rotating around a vertical axis. So the radius is the distance from the curve to the axis, and the curve is farther to the right, so I'll call that curve x1. And the distance of that curve from the axis is x1 minus 0, because we're rotating around the x-axis. And x1 minus 0 is just going to be x1. And as I rotate it, it's going to trace out a circle of area pi r squared. And then if we want to create the volume, which would result from all the circles that would result, you would end up with like this interesting looking little shape. something like this. And that would be found by doing an integral, but with respect to y, because it is a vertical axis of revolution. And when you do with respect to y integration, you go from bottom to top, so that's from -2 to 1. And once again, if you're punching this into your calculator, it's going to look like this. Anything that's an x is a y and vice versa. And this equation here, which is what you'd be typing in under y1, would be written like this instead on your calculator. But this is what you should have written on your paper. So don't ever write this on your paper for an FRQ, because that would be wrong. But that's how we have to do it on our calculator. But this is how you write it on your paper. Okay, so let's go ahead and we'll take a look at the answer for that one. That'd be 49.009. And we're good to go. And notice, by the way, these answers that they're giving, they don't, I'm just being lazy here. Instead of putting the function y squared plus 1, which is up here in here, which is what you could do, I'm just calling that equation x1, and that's what I'm putting here, just to save myself some writing. All right, let's go ahead and move on to the next one. All right, let's take a look here. So this time, we're rotating this shape around, it looks like, the y-axis. Now, unlike the last two, maybe 4 problems actually, you'll notice that the shaded area is not touching the axis of rotation. And so that's going to result in a solid, but it's going to have a hole in the middle of it because that's not getting included in the rotation process there. So when that happens, this is what we call the washer method. And the washer method can be found by identifying the two functions between which the area is created. So I have that function there, which is represented by this, oops, wrong color, by this line right here. That's the line x equals 2. And then we have this function right here, which is this one right there. And this blue shaded region is the area in between those two blue curves. Okay, and you might think, Mr. Bailey, well, why isn't it the area between this top line and the red line? And that's because we're integrating with respect to y, so it's right and left. Okay, so the rightmost function is this green one, the leftmost function is the red one, and the radius of the circles, well, actually there's two different radiuses when you're doing the washer method. First of all, we have the radius of the green line. How far away is that green line from the axis of rotation? In other words, the y-axis. How long is that horizontal line? Well, we'll call that our big radius because that's the one that's farthest away from the axis of rotation. And the big radius is going to be equal to that function, which I'll just go ahead and call x1. I mean, you could call it just 2 if you wanted to. But it's x1 minus the axis, which in this case is 0, and therefore that would just be this. That's my big radius. Now, the little radius is going to be the line that's closer to the axis of rotation, like this one. This one has a radius from the red line to the x-axis there, and I'll represent that with a lowercase r, and I'm going to call that function, the red one, x1. So that one is also, I'm sorry, that's x2. x2 minus the axis. And there's your little radius. Now, as we spin this thing around the y-axis, the big one's going to trace out a big radius, while the red one's going to trace out a smaller circle. And basically, it creates a circle with another circle inside of it that represents like a hole it's tracing out. And so you end up with like washer shapes. And so we have the area of the big circle, which is pi big R squared, and big R is this. And then we have the area of the little circle that's being traced out, which is pi little r squared. And what we do is we're going to be, since that little r is cutting a hole out of the big one, we're subtracting those areas. Okay? And then what we're doing is we're integrating this. And since we're integrating with respect to y, because we are doing this on a vertical axis rotation. We go from the bottom point where they're intersecting to the top point where they're intersecting. And the way that I was showing this in class was I didn't really have the pi here or the pi here. Since they both have a pi, I just put one pi in the front of the entire integral like this. Now the top limit is pretty easy to see on this is 3, but the bottom one they don't tell us here. I'm seeing that, which is kind of unique. I haven't seen that yet. We'll try not to put one of those on your test, but for now, how do I find where those two lines cross? Well, hopefully you guys know that when you're trying to do these things by hand, the solution is to set those two functions equal to each other. So what I would do is I would take 2x1, the x1 function, and set it equal to the x2 function. The x1 is 2, the x2 is 1 over y. And so if I were to solve this for y, multiply both sides by y, you get 2y equals 1, and then divide both sides by 2, and you get a half. And so you can find where those two lines cross in that fashion if you ever need to, just by setting them equal to each other like that. Okay? But either way, once you go ahead and punch that into your calculator, you should get the following answer, 26.18. Okay? Now, if you are, when you're trying to put this into your calculator, once again, you got to keep in mind a couple of things. First of all, you're going to type that in like it's y1 equals 2, right? And you're going to type this in like it's y2 equals 1 over x, right? Because anything that's a y becomes an x, and an x becomes a y. Because our calculator only does things in terms of x, right? And then for your integral, instead of having here x1, you're going to have y1, and here instead of x2, you're going to have y2, and over here instead of dy, you're going to have dx. That's the only difference on the calculator. But once again, those are not things you want to write down on your paper. Those are things you want to type into your calculator. Writing them on your paper would actually be wrong. This is what you'd write down. All right, so let's go ahead and move on to our next question there. All right, looks like we got another one here that's kind of similar. Matter of fact, it's painfully similar to the last one. So much so that I'm going to encourage you guys to go ahead and look at the last example, and you just try to do this one and see if you guys can get the answer. Okay, now I'll tell you the answer real quick. You guys should be getting about 123.15. Okay, I think the tricky part on this one would be to ask you guys to see if you could find this point down here, but I showed you in the last problem how you can find where two functions intersect by hand if you need to. You could also do it on your calculator, actually, but that might get a little confusing because these are functions that are graphed in terms of y, and when you graph it on your calculator, it's going to be in terms of x, so it's going to look like the picture's been flipped somehow. So it'd probably be easier just to do it by hand. It's not too hard. All right, let's go ahead and move on to our next question. All right, so now I want to rotate this tiny little blue space here around this axis so that, once again, notice how the blue area is not touching the axis. And when that's the case, you're going to get a washer, which means you're going to have a volume on the outside, but a big hole, in this case, a really big hole on the inside. And so now, since I'm doing this one around a horizontal axis, everything's with respect to x. So my equation should be in terms of x, and my integrals are going to be in terms of x. Now, for the washer method, when you're doing these with respect to x, your two functions will have one that's farthest away from this axis. That would be the one on the highest function. And then the one that's close will be the one below it. And those are the two functions that create two different radiuses. So the radius of the red function is the distance of the red function from the x-axis. And so that's just going to be found by big radius is equal to the function, which I'll call that y1, this guy right here, minus the x-axis, which is 0. And that just simplifies to this. Okay, the little radius, which I should probably use a different color for, go ahead and do green. the little radius, we want to find how far away that is from the x-axis as well. And so the little radius will be equal to the second function, this guy right here, which I'll call y2 minus the axis of rotation, which is the x-axis, so that's 0, and that one's y2. And then finally, we're ready to go ahead and calculate the area of these circles as we rotate them around the axis. So the red one's going to trace out a pretty big circle here as we rotate it around the x-axis. And this green one's going to rotate a slightly smaller circle inside of that, creating like a donut-looking shape, which we call a washer. And each one of them has an area of pi r squared. This is for the big radius, or the bigger circle, and this would be for the little radius, giving us the little circle. And we want to find the volume that results from the area, which is just going to be this region here, this shaded region, the donut shape, because only that little blue space is going to be tracing out an area as we've rotated around the axis. And so that creates a hole because we're subtracting the little area from the big area to create a donut shape, right? And then as we integrate from here all the way back, it creates a solid, okay? And since we're integrating with respect to x, we integrate from left to right, right? So we start at 0 and we end here at 1. And as I did it in class, I didn't have the pi's in here twice. I just factored the pi out because it's a constant multiple on both of those pieces and put it in the front like that, which is how you can do it as well. But anyway, you're going to go ahead and type this function in for y1, type this function in for y2, and then type this into your calculator exactly as it appears, and you should end up with an area, or sorry, a volume of 18.326. All right. Here is our last one. So I want to rotate this little region here around the x-axis. So I'm going to be integrating with respect to x, and my equations should be in terms of x, which they are. So let's see here. The function that is highest will be the one that's farthest away from the axis of rotation, and that's the one that's going to give me my big radius. So that's going to be this parabola here. So my radius for the big circle is going to be y1, so I'll call that y1, minus the axis, which is 0. And then we have the little radius will be the distance of this other function here, which is closer to the axis of rotation, which we're going to call y2 minus 0. And that's that guy there. All right. And we're going to integrate that with a pi on the outside, squaring both of the radiuses, the big one first squared, minus the little one next squared, with respect to x, because we are going around a horizontal axis, and we're integrating from left to right, -2 to +1. And that would give us some kind of a strange looking like bowl almost, with a hole in it. If we were to rotate it around the x-axis as a result. But answer for that one would be 96.133. And that does it for our study guide review. So hopefully that was helpful, and we'll see you guys in class. Have a good one.